everyone. Today we are going to talk about second-order linear homogeneous differential equation. A really long name. Well, it's basically moving from first-order differential equations to the second order. And to make a first-order equation second order is that we'll include the second derivative into the equation. So what is a linear second-order differential equation? It will be something like you have a function, say random a of x, times the second derivative of y. This derivative is really ugly. Plus, you have some other function times the first derivative of y, and you have a third function times just y equal some other function. So just review our terminology. Y is second order because the highest derivative here is second derivative. So that makes it second order. So what makes it linear? Well, all of the coefficient. So when I say coefficient, in this case, I mean it was either a constant or it's a function. In order for this to be a linear differential equation, a of x, b of x, c of x, and h of x, they are all function of x and only x. Or they could all be constant. Or they could all be a function of another variable that's not y. The thing is, they have to be the same. Okay, so now we know it was linear. How do we know it's homogeneous? Well, you probably heard about the word homogeneous when you are learning the first order linear differential equation, but in this case, they are different. Yes, they are all called homogeneous, but they are not related. Really, they just use the same name, and I still don't understand why do they do that to our poor students. Anyway, in this case, when I said it was homogeneous, it means that h of x equals 0. Yeah, that's how it works. It will be equal to 0, and then it's homogeneous. So a general form for second order linear homogeneous equation would just be a times y, b times y prime plus cy equals 0. As you see, I changed out the function coefficient into constant. Well, it's for learning purpose. It's not like I was trying to take a little bit less workload when I was doing on the proof. Okay, despite its ridiculous long name, it's actually one of the funnest way, or actually the most simplest differential equation you can use to solve because it can all boil down into algebra. Before I prove this for you, we will first think about some property so you can make my proof process easier. Y equal g of x. So g of x is a solution to this question. And then is some kind of constant times g of x also a solution to this? Well, we can plug it back in. Say g prime prime of x. So this is the proof process, and it's just basic algebra. Let's just quickly get through it. Like, c is a constant, right? It could be any constant. And we know these things from the first equation is 0. So c times 0 will be 0. So any constant times the solution will still be the solution to this question. Okay, so we get the first property. Now let's look at the second property. I said y equal k of x is the other solution to this equation. Then can you tell me if g of x plus k of x is a solution to this equation? So let's check it out using algebra. Yeah, first we separate it, then we rearrange it. And do you see what we get? So we know that this part in front is 0. And we know this part, since k is another solution, then this is also 0. 0 plus 0 equals 0. This is the second property of a solution plus another solution is also a solution. The third property will be that if you have y equal gx as a solution, y equal x times g of x, or x to nth powers times g of x. will also be a solution. But for time purpose, I will not show it here. So let's get started on making the calculus algebra. First, we need a question. So we need to assume y to be something. But I mean, if you assume y to be any kind of function, its second derivative and like first derivative will just be different. So there was one really amazing equation, e of x, and its second derivative and third derivative will be the same. But if you just said y equal e of x, this is going to be wrong, because e of x minus e of x minus 6e of x, there was no way it was going to be 0. But I really want to use this property. So what should I do? Well, let's say we can set y e m to the x. So y prime will just be m e m to the x. Y double prime will just be m squared e m to the x. And when we plug it in, there's a small algebra manipulation. What can you tell? There was no way e of m of x will become 0, but there will be 2m for m squared minus m minus 6 to be 0, right? And since it's converted from the original equation using algebra, we both this really hard calculus question into algebra. So theoretically, y to some sort of nth derivative can just be m to the n squared, or m to the, like, say y to the second derivative is m squared, y to the third derivative would be m cubed. And believe it or not, this is actually the classic way you use to solve nth order linear differential equation. Of course, n was bigger than 1. But anyway, today our focus will just be on the second order. And do you know how to solve this m squared minus 1 minus 6 equals 0? I think quite easy, right? And you will get m could be 3 or m could be negative 2. So what would be the answer? Well, y could be either m 3x or y could be either e negative 2x. So what's the more general term? Well, we learned from a minute before, or maybe several minutes before, that if you times a constant in front, it will still be the solution. And then we say that if y gx is a solution and y kx is a solution, then gx plus kx is also a solution. Therefore, the most general term of the solution will just be y c1 of e to the 3x plus c2 e to the negative 2x. So who said what we see is not algebra? Okay, alright. So say we are focused on second order, but when we are writing those equations, we actually know that m squared plus, bn plus like c equals 0. There is different kind of solution, right? When we are learning algebra, we learn that when we are solving it, we said that negative b plus and minus b squared minus 4ac over 2a will give us solution. But this could give us, two real solutions, or a repeated one real solution. And also two non-real solutions that involve something called I. So what should we do when we encounter that? So remember our basic format? Y was equal to E m of x. And say we have two distinct real solutions, m1 and m2. Then our solution, like we'll be showing last example, will just be this. And if we are going to more order, like nth order, that's what's going to happen. But alright, let's focus. And when you have a repeated real solution, say you get m1 and m1, then y will just be ce m1 to the x. But for the second one, you don't really want to repeat it. So you times the x in front, and then that will be your solution. Up to now, we're still following the three property we talked at the beginning, but for the last one, the two non-real solution, it would just be a little bit harder to explain. There was general solution to it, and for a complex number, up to this point, just remember this equation. So say you have alpha plus b of x, and 2 equal alpha plus alpha minus b of I. Then your solution will be C1 e alpha x cosine bx plus C2 e alpha x times sine bx. This is for a complex root. So now we know how to, do those kind of questions. Shouldn't we try an example? Pause right now to try it out. Ready? Okay, now I'm going to show you my answer. We have two complex zero, and our general solution will just be ta-da! So now let's look at some real life example. Well, why do we learn math? Because we want to see real life application. As I say, this is classic for basic physics. And one of the many applications of linear differential equation is describing the motion of an oscillating spring, according to Hooke's law. A spring that will stretch like y unit from its natural length L tends to restore itself to its natural length by a force of F that's proportional to y. So y was basically like, displacement. You know what? Let me write it out. So the force of a spring was like proportional to the displacements and its spring constant, negative spring constant. So in here we said the changing x was y of t. We are describing a string that was oscillating. And then here the t stand for time. So oscillating throughout time. It's like you pull a string downward, I will keep oscillating. If you just use changing x, that's like AP physics D, and the spring was not moving. It's just at equilibrium with the gravity. Talking about equilibrium, if there was only two forces in the system, then the force going down is same as the force going up. So the box would be in constant, not moving. And the only force going down in this closed system was the gravity that was pulling down, which is mg. And then here the g was like acceleration. And the force pulling up was like the spring. And say this system was like keep moving, but still there was only this two force playing the show, then acceleration will actually be y double prime of t. Instead of I would use g here because the acceleration is also constantly changing. It will be the force going down minus the force going up if we consider going down is the positive direction. And since we know y of t is the displacement, y double prime of t acceleration. So using algebra, we can set up this equation and doesn't this look familiar to you? I mean, m and k is just constant. Isn't this the second linear homogeneous differential equation? Okay, finish explain the basic mechanics. Let's try a practice problem. So we know it's like not all theoretical. Well, this is theoretical because in real life there will be other force. Anyway, let's start with a question. System with a spring going down carrying a 4-gram weight. And then this is before the system start oscillate, so it's at equilibrium. And at equilibrium, the spring was naturally displayed for a meter. Then a random key can pull the block down for 6 meter and then release it, so it will bump upward and start oscillating. So let's find the formula of the position of the weight as a function of times t. We just call it y of t, which will be position. So let's first get the spring constant, and we know that when it was not oscillating, which is at equilibrium, the gravity was normally like negative 9.8, but in this case we'll use negative time. So 4 times negative time is the weight. And then we know that the spring constant will be negative k times the changing position. And remember, the things was not oscillating yet, so the displacement was just 8. And we can cancel the negative on both sides. And then it's just basic algebra. We get 5 equal k. When the system start oscillate? So when the system start oscillate, we can no longer use g, we use y double prime, because as we say, the acceleration downward is constantly changing in respect to time. And to make it simplify, we will just say double prime of t was just y double prime. So now we set up the equation. Now we are playing with algebra. We just set divide m from both sides. K over my equals 0. K we know is 5, and m we know was just the mass was 4. So I guess now we have equation to solve. Let me clean up the space and time to use our algebra skill. Okay, we get complex 0, and then we can tell alpha was 0 in this case, and beta was like square root of 5 over 4. So the position of the object oscillate over time will just be e to the 0x, which is z to the 0, which give us 1. So we don't need to write it. And cosine square root of 5 over 4x plus c2 sine square root of 5 over 4x. Which you can see actually makes sense since the string was oscillating, and we know normally in oscillating version we are going to use sine and cosine. Not really unexpected, right? Now we are going to use the initial condition. So at the beginning you already have a displacement of 8, then you put it down for 6 more meters, so at t equals 0, your displacement was 14. Cosine, anything times 0 is just 0. So cosine of 0 was 1, and sine of 0 was 0. Therefore, 14 equaled C1. So how do we get C2? Well, normally in those kind of questions, it will tell you the initial velocity after you release the spring, and it will go right upward and will be that velocity. However, this question only asks for the general form, so it do not really offer us a velocity. But I want to give a more thorough example. So I make up a velocity called bm per s. Of course, b could be negative or it could be positive. Since we assume in this case down was, positive, so b was probably negative, but it's alright. We can solve it. So since y was the displacement, y prime will just be the velocity. And the initial velocity we said we assume it was b. And what was y prime of t? Well, you have y of t, you just take its derivative. It wasn't that hard. And you plug in 0 to get with t at 0. Y prime equals 0 equal b. And we know that sine 0 will become 0, so this part do not matter. And this cosine 0 will just be 1. So b will equal to square root of 5 over 4 c2. So c2 will just be, or you can say 2b over square root of 5. Now you have c1, you have c2. So in this scenario, y of t will just equal to 14 cosine square root of 5 over 4t plus 2b square root of 5 sine square root of 5 over 4t. Now we know how to solve the second order homogeneous second differential equation. It will be much harder when it's non-homogeneous. But that's a term for next video. Thank you.